Alright, so in this video I'm gonna be explaining a two-stream AMR-enhanced model for document level event argument extraction. First of all, our event extraction method is document level instead of sentence level, which is a traditional approach. Document level is much harder. Instead of dependency parsing, leveraging syntactic parsing, we are using semantic parsing like AMR, abstract meaning representation. And we train it as a two-stream AMR enhanced model. So this is a paper in 2022. Most previous studies aim at extracting events from a single sentence, while document-level event extraction still remains underexplored. In this paper, we focus on extracting event arguments from an entire document, which mainly faces two critical problems: the long-distance dependency between trigger and argument over sentences, the distracting context towards an event in the document. To address these issues, we propose a two-stream abstract meaning representation enhanced extraction model. It encodes the document from different perspectives by a two-stream encoding module to utilize local and global information and lower the impact of distracting context. Besides, TSAR introduces an AMR-guided interaction module to capture both intrasentential and intersentential features based on locally and globally constructed AMR semantic graphs. So you see here is a document from RAMS dataset, and a transport event is triggered by shipment with 5 event arguments scattering across the document. It's not just one sentence, it's across the document. So the distance between the trigger and entities are very long. So in order to take advantage of the essential context and avoid being misled by distractions, we introduce a two-stream encoding module. It consists of a global encoder that encodes global semantics with as much context as possible to gather adequate context information, and a local encoder that focuses on the most essential information and prudently takes the extra context. In this way, TSAR can leverage complementary advantages of different encoding perspectives and therefore make better use of feasible context to benefit the extraction. Besides, to model the long-distance dependency, we introduce an AMR-guided interaction module. Abstract meaning representation graph contains rich hierarchical semantic relations among different concepts, which makes it favorable for complex event extraction. So here we have global AMR graph, but here we have local. And then we have a fusion which combines them, and we have extraction loss, and because we have boundary loss as well. Then the final loss is a combination. So the document is fed into the two-stream encoding module, followed the AMR guided interaction. So you see this AMR guided interaction, because first we have a local encoder and a global encoder. We have, for example, 3 sentences, and this is a two-stream encoder module. That's why we are talking about two-stream encoding module, that although more context is provided by the document, it also inevitably introduces irrelevant and distracting information towards the event. These noise signals can be harmful to the argument extraction. To capture useful information and filter distracting one, we propose a two-stream encoding module consisting of a global encoder that is aware of all context and a local encoder that only prudently focuses on the most essential information. Therefore, we can leverage their complementary advantages to make better use of context information. So the global and local encoders share the same transformer-based pre-trained language models such as BERT. By controlling the reception field of the words in the self-attention module, we can encode the document from different perspectives. In global encoder, the attention technique is the same as traditional transformer. So query times key, transpose, and then values. But here we have query and keys plus one mask matrix. Here is a mask matrix. Because here is local, but here is global. But in the local encoder, we introduce a mask matrix such that tokens can only attend to the sentence itself and sentence where trigger locates to avoid redundant, distracting information. So we encode the document with two different streams, a global encoder and a local encoder. One key challenge to extract argument from document is to capture intrasentential and intersentential features. Therefore, we propose an AMR-guided interaction that adopts abstract meaning representation. And in my playlist for semantic parsing, I have explained AMR approach. So AMR semantic parsing models the meaning representation of a sentence as a routed, directed, labeled graph. There are some parsers that are free. You can use it. You don't need to just train your own AMR parser. Just take advantage of current parsers, like dependency parsers that you just take advantage of. Stanford Core NLP, Spacey, Size Spacey, Allen Institute for AI. They are very different free parsers. So the AMR guided interaction module is attached after the global and local encoders, and we use the AMR graphs as skeletons for information interactions under a composition, interaction, and decomposition paradigm. From the local perspective, we construct AMR graphs for each sentence in the document, and they are isolated from each other. For initialization, the vector representation of node is composed by averaging the local representations of its corresponding text span. So just take the average of local spans, and then we use L-layer stack graph convolutional network to model interaction among different concepts. So we have layer L, and then we update for the next layer. Finally, we concatenate the vectors in all layer and derive the final node representation. Then H sub U is decomposed into local representation of corresponding words. From the global perspective, we first construct the global AMR by fully connecting the root nodes of different sentences, since root nodes contain the core semantics. Then similar graph-based interaction methods are used to obtain the AMR-enhanced global representation. So this is an example of AMR graph which provides abstract and logical semantic information, where the nodes denote the concepts and the edges refer to different relation types. So we use a gated fusion to control how much information is incorporated from the two-stream representation. So given h sub I g tilde and h sub I l tilde, we calculate the gate vector. G sub I is the gate vector with trainable parameters. So we learn it like this. It's a sigmoid function of this linear network. Then we derive the fused representation, hi sub tilde. Now that we have the fused representation and start and end, then we can create the span for candidates text span ranging from I to j, omega I to omega j. Its fused representation consists of the start representation and the end representation and the average pooling. So the third argument is your average pooling of hidden states of span. Finally, you get but boundary loss is defined as a cross entropy loss. And for classification loss, we use this. So finally, we train the model end to end. We have classification loss and boundary loss. And so this is an extraction case. First, it's a two-step process. And you see the trigger, you see the argument rows. And this is the data set that, because it is in the text level, not sentence level, we use this data set, which has about 3,000 documents, 7,000 events, and 17,000 arguments. And you see the state-of-the-art accuracy is still low, 58, because of course this problem is even harder, especially for this data set which is at the document level. But for the wiki events, it is a little bit easier. That's why we have high accuracy.